Okay, these are the theories about the origin of Earth. We have planetesimal theory by Chamberlain Moulton, tidal hypothesis by Jean and Jeffrey, nebular hypothesis by Kane and Laplace, interstellar dust hypothesis by Schmidt, supernova theory by Hale, Big Bang theory given by many, the most prominent are Gamow, Delametre, and Hubble. So we're going to Earth's composition. Earth is very complex and diverse. It's not a single rock. It has a layered structure with inner inner layers being heavy and outer layers being lighter. This is best explained by nebular hypothesis of Laplace. According to it, Earth was a gaseous nebula. Later, it condensed, and through a process called gravity accretion, where denser materials are inward and lighter materials are outward. So D1 greater than D2 greater than D3. It resulted into planetary accretion. So it resulted in density stratification or differentiation, which is this thing. So basically the earth is made up of elements which make up the minerals, which make up the rocks, which make up the earth. So the most abundant elements are iron, oxygen, silicon, magnesium, aluminum, and nickel. And the minerals, the silicate minerals are most abundant. There are other minerals also. The important silicates are quartz, feldspar, orthoclase, plagioclase, muscovite, biotite, amphibole, pyroxene, and olivine. These are non-ferromagnesium silicates, which are also felsic. These are mafic or ferromagnesium silicates. Compare these both. These are lighter, these are darker, these are less dense, these are more dense. These are acidic, these are basic. They have iron and magnesium, they have calcium, potassium, and sodium. So the felsic minerals are seen up to 60 kilometers, mafic up to greater than 100 kilometers, mafic are more abundant. So mineral versus rocks, these are compounds, these are mixtures of minerals. They have a different composition. This doesn't have any such thing. These are the basic building blocks of the earth's surface. These are aggregates of minerals. Silicates are the most abundant minerals. Rocks, we have igneous, sedimentary, and metamorphic. Igneous rocks, we have granite, basalt, andesite, rhyolite, gabbro, and diorite. Sedimentary, we have sandstone, breccia, conglomerate, and shale. Metamorphic, we have slate, phyllite, schist, marble, and gneiss. So igneous rocks, according to silicon content, we have two types. We have two types, intrusive and extrusive, depending on where magma cools. If it's inside that, it's intrusive. Outside the surface, it's extrusive. So the most important rocks are based on silicon content. Extrusive are rhyolite, andesite, basalt, and comatite. Intrusive are granite, diorite, gabbro, and dunite. The most abundant ones are granite, andesite, basalt, diorite, and peridotite. Now coming to Earth's internal structure, Earth's interior is layered. This is explained by the nebular hypothesis. And as the depth increases, density also increases. Therefore, outer layers are much dense. They have felsic or non-ferromagnesium silicates. Outer layers are more dense. Inner layers are more dense, and they have mafic or ferromagnesium silicates. So earlier models, they were based on speculations which are given by Edward Suess, Arthur Holmes, and Van der Graaf. CLC knife is a model given by the Edward Suess. Modern contemporary theories, there are two types, which are chemical layering and mechanical differentiation. Chemical layering, it talks about composition of rock minerals and gives three layers: crust, mantle, and core. And they have oceanic crust and continental crust, outer, middle, inner mantle, outer and inner cores. According to mechanical differentiation, we have lithosphere, asthenosphere, mesosphere, and barosphere. These two together are called pyrosphere. Lithosphere is made up of crust and upper part of upper mantle. Now let's get to chemical layering of Earth's interior. There are two types of crust: oceanic crust and continental crust. We can see it here. Oceanic crust is thick. It is 60 kilometers thick. Some places it's 80 kilometers thick. Oceanic crust is thinner, 1 to 3 kilometers. This is lighter, this is darker, this is less dense, this is more dense. These are made up of non-ferromagnesium silicates or felsic. These are made up of ferromagnesium silicates or mafic. So obviously we have quartz, feldspar, orthoclase, plagioclase, and mica. Here amphibole is the most abundant mineral. Some pyroxene is there, no olivine is there. Olivine will be there in the mantle. So this is hard and brittle. This is relatively softer. These are acidic and intermediate. These are basic. The igneous rocks found here are granite, andesite, rhyolite, diorite, plus sedimentary rocks are there. And here only basalt and no sedimentary rocks are there. So this is the structure. Now coming to mantle, the density is 4 to 4.5, but the inner mantle will have 9 to 11 density. And obviously density increases with depth. The minerals found here are ferromagnesium silicates are ultramafic. Olivine is found in the upper mantle, and these are found in the deeper mantle. What are they? perovskite, spiral, spinel, and garnet. The rocks found here are peridotite and dunite. So the outer mantle is up to 350 to 400 kilometers, middle up to 700 to 900, inner mantle up to 2800 kilometers. Upper mantle, the most abundant mineral is olivine, which has a special property called semi-molten. Because of this, it flows as a liquid. The core, the density is greater than liver, so it is very dense, it is very hot. So outer core is up to 4800 kilometers, inner up to 4800 to 6400 kilometers. So the core is very dense, the density is greater than 11, it's very hot, 3000 to 5000 degrees centigrade. We have seen outer core and inner core 2800, 4800, and it has abundance of nickel and iron. The outer core, it is molten because of silicon impurities along with the nickel and iron. The inner core is relatively pure, therefore it is solid. So this setup results in something called geomagnetism. We'll see it later. The entire structure can be seen here. So this is a continental crust, this is the oceanic crust, this is the upper mantle, middle mantle, inner mantle, outer core, inner core. It's 350 multiplied by 2, 700 into 4, 2800, and we can remember 4800 and 6400. Now we are going to the mechanical differentiation. Based on type of composition and how they behave, some layers behave as a single unit. This is the mechanical differentiation. So these layers are lithosphere, asthenosphere, mesosphere, and barysphere. Lithosphere consists of crust and upper part of upper mantle. Asthenosphere consists of rest of the upper mantle. Mesosphere consists of remaining mantle, and barysphere consists of the core. Therefore, the depths are 100 kilometers, 350, 2800, and 6400. So the lithosphere is brittle, it's cold, and it's not continuous. Therefore, it is broken into something called plates. So there are 3 types of plates: oceanic, continental, and both. They are floating over the semi-molten asthenosphere because of the olivine. Now there are some other models of Earth's interior which are given by Edward Suess, C.L. Seaman Life model. The depths are 300,000 to 2,000, 6400, and the specific densities are 2 to 3, 3 to 4.7, greater than 5. And this contains continental crust, this contains ocean and mantle, this contains the core. The model given by Daly and Arthur Holmes, it's about silicates, outer, intermediate, and inner silicates. This consists of mixture of the igneous rocks we talked about, grandiorite, amphibolite, echolgite, and peridotite. So the depths are given here. And the Van der Graaf model, it is very close to our contemporary understanding. Outer silicates, inner silicates, mixed silicates, inner metallic layer. Depths are 60 kilometers, 60 to 1100, 1100 to 2800, greater than 2100. The first thing consists of only continental crust. It consists of upper and middle mantle. It consists of middle and inner mantle. This consists of core. Now we are going to the conditions of Earth's interior. Based on the density and rigidity, the crust and outer layers are solid and brittle. Asthenosphere is semi-molten. Mantle layers are dense and relatively softer. Outer core is fluid, as we talked about. Inner core is solid. The molten magma circulates in the mantle. This is called as convection currents. This is given by the Arthur Holmes. So this is something how the convection currents happen. And coming to the temperature, within the lithosphere, up to 100 kilometers, the temperature rises at 2 to 3 degrees centigrade per 100 meter. Beyond that, there is no uniform pattern. At tectonic locations, very high temperature of 1000 to 1500. Asthenosphere has 1000 to 1500, deep mantle has 2000, core mantle boundary has 3000, and core has 4000 to 5000. So where does this heat come from? 2 sources: radioactivity and residual gravitational heat. This is from the nebular hypothesis, from the solidification of ancient nebula. Radioactivity through fission reactions. So there are certain discontinuities. These are the layers that separate the distinct zones like lithosphere, asthenosphere, core and mantle, etc. So the Moho separates the continental, the crust and the mantle. So there are 2 types of depth. It is shallow at oceans and deep at continental. And repetitive birch, it is debated whether it is there or not. So it is between middle mantle and the inner mantle. Gutenberg is definitely there. It separates the mantle and outer core. And Lehman separates the outer and inner cores. The Conrad discontinuity separates the continental crust, the more felsic part and less felsic part. It is not present in the ocean because ocean is too thin for any such separation. So the evidences of Earth's interior, the Earth is very deep, 6,400 kilometers. So we do not have direct physical evidences. So most of our inferences are from the indirect extrapolations, and very few are from direct observations. Some of the direct evidences are volcanoes, mines, meteorites, deep trenches. So remember this South Sandwich Trench at South Atlantic, where mantle is exposed. The indirect studies are two types: density studies and seismic wave studies. This is not important. This is important. Seismic wave evidences. Whenever there is an earthquake, there is an energy release. There are two types of energies released: radiations and mechanical waves. These are gamma waves, IR, etc. So they do not require any medium to transmit. So these are not important for our studies. And the mechanical waves, these are set of vibrations and they need a medium to transmit. So based on the properties of these waves, we can understand how the composition of medium is, that is density and rigidity. So we were looking at seismic wave evidences of Earth's interior. Whenever there's an earthquake, there's an energy release. So there are electromagnetic waves and mechanical waves. These are not important. Mechanical waves, since they need a medium to transmit, if we study the properties of these waves, we will get to know the properties of the medium. So there are two types of seismic waves basically, which are surface waves and body waves. Surface waves are of two types: Rayleigh waves and Love waves. These are very destructive since they do not travel to the body. These are not important for studying the Earth's interior. Body waves, on the other hand, they travel to the interior, therefore they are important for studying the Earth's interior. We have two types of body waves: P waves and S waves. These are primary waves and secondary waves. These are longitudinal, so the particle motion is parallel to the wave motion. Here the particle motion is perpendicular to the wave motion, hence they are transverse. These are like sound waves. These are like the plucked string of a guitar. So a few properties of the body waves: the velocity depends upon the density and rigidity, so it is a function of both. When they vary, the velocity will also vary. S waves, they cannot travel to the fluids. P waves, they can travel through, but they will slow down. Now we'll look at the behavior of these waves and what can we infer about the interior from that. So at the shallow depths, the velocity is very slow, 4 to 5 km per second. This is because of the upper granitic layer has low density. So these waves are called PG and SG waves. At 30 kilometers depth, we have Conrad discontinuity, which separates the more felsic and less felsic part. Hence the density variation. Because density is increasing, the velocity will also increase to 6 to 6.5 km per second. They are called P and S waves, intermediate P and S waves now. At Moho discontinuity, it doesn't have a specific depth because it varies according to the ocean and continental crust. Velocity will suddenly increase to 7.5 to 7.8 kilometers per second. These are called P star and S star waves. There is more discontinuity. Velocity increases because mantle has higher density. At 100 kilometers depth, there is sudden slowdown to 7 to 7.2 kilometer per second. This is because of asthenosphere. Asthenosphere has very low rigidity because it is semi-molten. Though the density increases, because rigidity is very low, the velocity will decrease. Hence, asthenosphere is also called as a low velocity zone. At 350 kilometers depth, asthenosphere ends. Hence, there is a increase in velocity to 9 km per second. Hence, deep mantle is called high velocity zone. At 2800 kilometer depth, S waves will disappear and P will slow down. The velocity is very slow. This shows us that outer core is completely fluid because of the silicon impurities. Since S wave is transverse, it cannot pass to the fluids. If you look at this diagram, here we have the Conrad discontinuity. The S and P waves are slow. At Moho, after the Conrad discontinuity, velocity increases. After Moho, it increases further. Astheno, they will slow down, hence LVZ. After that, the velocity will increase very much, hence it is called high velocity zone. Later, S wave will disappear because outer core is fluid. Later, the P wave refracts, showing us that inner core is solid. So this is the S shadow zone and this is the P shadow zone. Remember 103 and 143. Because inner core is solid, the P waves will refract, hence this will be the shadow zone for P. Since P and S waves are continuously bending from here to here, we can infer that with depth, density also increases. And the P waves bend at the inner core. Therefore, we can say that inner core is solid. So these are some fold mountains. So the Archean mountains are Aravallis, and we have Eastern Ghats. Proterozoic mountains, we have Vindhyas. Caledonian mountains, we have Jolene in Norway. Hercynian mountains, we have Appalachians, Urals, and the Great Dividing Range in Australia. Tertiary mountains, we have Rockies and Andes. Here we have Alps, Pyrenees, Atlas, Caucasus, Himalayas. Coming to continental drift theory, we have some fundamental questions about the Earth, which are: how did Earth form? What created oceans and crust? How did crustal differentiation, that is, why is ocean and continental crust different? Uh, how did the continents come to be where they are at? What factors decided it? What was the nature of the initial crust or the primordial crust? We need to explain the features like volcanoes, islands, earthquakes, and fold mountains. Fold mountains have some special features like they are only unique to Earth, they are not found on other planets. They are very tall and very large. They have marine sediments, interestingly. Some of the earliest theories they mention that continents are permanent and immobile, but this does not explain fold mountains, earthquakes, and volcanoes. Some interesting observations with respect to continents. Francis Bacon and Benjamin Franklin observed that Africa and South America's east and west coast they fit perfectly. This is called jigsaw fit. And Snyder in 1800s he talked about similarity of coalfields in US and Western Europe. So we can see Appalachian mountain coalfields, Newfoundland coalfields, and Pennines mountains in Britain. And Taylor in 1908 he gave one of the earliest interpretations of continental drift. According to him, there were two supercontinents, Laurentian Gondwana land in north and south. In between, there was the massive sea called Tethys. Due to some factors, they both came together and the sediments got pressed up and turned into the east-west Trans-Eurasian mountains. Now we'll look at the ideas and contributions of Alfred Wegener. Alfred Wegener, he was a climatologist. His aim was to discover its past climate history. He studies three things: rocks, fossils, and sediments. Plus, he used the works of the Francis Bacon we have seen here, Snyder we have seen here, and Taylor we have seen here. He has put together all these observations and gave his continental drift hypothesis in 1912.